Hello and welcome back to the linear algebra series. Let's talk about span. So we recently talked about dependent and independent vectors, and this directly correlates to span. So the span of a set of vectors can be thought of as all of the possible combinations of certain vectors in a space. So we recently looked at this example in the past video. So that was, let me just make sure I get this right. V1 was this. And V4 was, apologize, I'm running out of space here, 4, 8, 8, 15. Okay, so this is our set of vectors. They're a little crammed, but let's not worry about that. So we determined that these two vectors, V1 and V2, were the linearly independent ones, meaning that we can represent these in terms of these. So if we were to look at every single possible vector that we could make out of these four vectors, we would only need these two vectors, since these would be in the span of these two vectors. So the span of a set of vectors is given by x1, v1 plus x2, v2 plus dot 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 plus xn vn. So the span of this space only takes into account of these vectors. So our span is actually just this. x1 times our v1, 1, 2, 4, 7, plus our x2, 2, 4, 0, 1. And this makes sense because we know that these vectors are in this space, and we also found out in the last video that V3 is V1 plus V2, so our x1 and x2 are 1 and 1, and our V4 is 2V1 plus V2, meaning that they're in the span. And any possible combination of these vectors is what we call the space of these two vectors. And that's it for space, or span, sorry. That's it for vector span. So the span of this space is this right here. So thanks for watching. I hope to catch you in the next one. I hope this was very helpful.